I've started recording again. We just left at the spot where we have a structure from both ends. Similar priority substituents are there. Where are you going to start your numbering from? You will start your numbering now from the lower alphabetical system. But always remember, before you go for alphabet, go for the lower locant value. With this information, let's just do one question, just to remind all of you what we will be doing. And go ahead and draw this structure on your pages also, in your notebook. And make sure that you draw the exact same number that I have. 1, 2, 3, 4, 5, 6, 7. And then we have these branchings right here.
I have a question.
Yes, please go ahead.
It might seem kind of slow, but what's the difference?
I'm sorry, I'm not able to hear you. Could you speak up a little loudly?
Can you hear me?
Now I can, yes.
What's the difference? Like, you know how we have octets and then we have like the bonds. Like, how do we know? Like, say carbon. Like, we know that carbon has 4 bonds, but what's the difference between that and then the octets? Like the lone pairs that they have. That I'm confused about that.
I'm so sorry. You would have to repeat your question. I only heard what is the difference between, and then I could not hear anything. Could you repeat the question again, please? What is the difference between?
Like the octets and the bonds, like I don't.
Octet in the bond. So this is a bond line structure. And if there are no positive charges or any formal charges or any negative charges, we will assume that the octet is complete. And as we studied in module 2, that each dot is a carbon. And even if we do not say it, each dot, this is a carbon. How many bonds it is already making? 2. And so there are 2 hidden hydrogens here. And we don't have to write out all the carbons and all the hydrogens. We only write non-carbon and non-hydrogen bonds. So for example, I have these 2 carbons, and at the third location I have an oxygen. Make sure this is module 2, okay? Do you understand this now? So the octet of this carbon is now complete.
Okay.
All right, okay. So coming back to this structure, how are you going to name this structure? We will follow our same rules. First, we are going to find our longest chain. All of you have drawn the structure. Let's go ahead and find the longest chain in this structure. So if I say that I feel this is my longest chain, let's go 1, 2, 3, 4, 5, 6, 7. So right now I'm not trying to find the locant value. I'm just trying to find my longest chain in the structure. So 1, 2, 3, 4, 5, 6, 7. So this gave me 7 carbons right here. But if I start 1, 2, 3, 4, 5, 6, if I had used this, then I would have gotten 6 carbons. Let's do this also. 1, 2, 3, 4, 5, 6, 7. So I can get 7 carbons from this pathway as well. 1, 2, 3, 4, 5, 6, 7. 7 carbons from this pathway as well. 1, 2, 3, 4, 5, 6. So this is 6 carbons. I can ignore it. 1, 2, 3, 4, 5, 6, 7. So this pathway can also give me 7 carbons. Any questions on how I was trying to find my longest chain? Any questions? Any doubts? So I have some options with 7 carbon chains. One is right here, one is right here, one is right here, and then one is right here. I'm not attaching these two because they are exactly similar. So I have figured out my longest chain. What must my longest chain have? It must have the priority of the molecule. Is there any priority on my molecule? There is no priority on my molecule. Even if you look at these methyl groups have similar priority. All these substituents have similar priorities. There is no alkene, there is no alkyne. So I don't have to start or make sure that my longest chain have those. But what must my longest chain have? My longest chain must have most number of substituents. So now is my chance to look. If I look at this 1, 2, 3, 4, 5, 6, 7, I will have how many substituents? I will have these 2 substituents. Do we all agree on this? If I choose this chain 1, 2, 3, 4, 5, 6, 7. If I choose this long chain, how many substituents will I have now? 1, 2, 3, and 4. Okay. Now this pathway is exactly same as this pathway, which I have right here, right? What about this one? 1, 2, 3, 4, 5, 6, 7. So if I had gone with this pathway, with this longest chain with 7 carbons, how many substituents would I have now? 1, 2, 3. So if I follow this route, I would have 2 substituents. If I follow this route, I would get 4 substituents. If I follow this route, I will get 3 substituents. So which is the route, or which should be my longest chain? The one with most number of substituents on them. Any questions? Okay. Now what is the next part in rule? I don't have any other thing to look for in the longest chain. What I must look now is the locant value. I need to have the smallest number for all my substituents. So I'm not going to consider this. I'm not going to consider this. I'm only going to consider this chain. Let me give numbering from here. 1, 2, 3, 4, 5, 6, 7. Or I can start my numbering from the other direction. 1, 2, 3, 4, 5, 6, 7. Looking at the numbering that I have given, what do you think will be the smallest number for all the substituents? Do you think I should follow the black path or I should follow the red path?
Red.
Michaela? Yes, it is red. Very good. We are going to follow the red path because we want our substituents to be the smallest in locant value. So let's see what all substituents do we have. We have a methyl here, a methyl here, a methyl here, and a methyl here also. And we have how many carbons in this? 1, 2, 3. So 3 carbons equate to a propyl. Any questions so far? And so now our substituents are M and a P. So we are first going to write our root name, right? What is our root name? If you remember how we figure out our root name, we have the number of carbons. Throughout, it is the alkane, and the priority will be E because there is no other priority. So 7 equates to what? What is the root number, or what is the root name for 7 carbons? Hept. Very good. Hept throughout hydrocarbons and heptane. Now out of M and P, we have to write them alphabetically. Equal priority substituents are written alphabetically. And if you have more than one of the same groups, we always put di, tri, tetra, etc. So how many methyls do we have? We have definitely more than one methyl in our structure. So we are going to write trimethyl for sure. And we have this propyl. So which of the substituents will I write first? The trimethyl or the propyl? First of all.
Methyl.
Okay. And why?
Alphabetical.
Very good. We are not going to consider the T. We are only going to consider the M. So at what locations do I have my methyl? At 2, 3, and 5. So 2, 3, 5. All numbers with separation of comma. Numbers and alphabets separated by a hyphen. No gap between any alphabets. Now, alphabet and number will have a hyphen for propyl. And so ideally heptane should be next to propyl, but if you have a little bit gap here on your drill test, I will not take points off. So don't be scared of that. As long as it is written clearly and completely, and I see the hyphens and the commas between.
I have a question.
Yes, please go ahead.
Okay, so I had it numbered the other way, so my methyls would have been
Go ahead.
I think
your method would be 3 and then 5.
5, yeah, and 7. 6, yeah. Was that okay?
No. So that is the rule. You need to have the smallest locant values.
Oh, okay, I get it. Gotcha.
Yes. So that is something that we have to remember. I mean, I know it's a little tricky, but why don't all of you try this one now? It's pretty simple. First, figure out the longest chain. Try it on your own. You will see. And I've placed the rules right here if you have to see them. Again, these nomenclature rules are in your sequence sheets also. You can print it out or you can rewrite them on your own. Whatever makes you feel that it will help you. Always remember that numbering will take priority over alphabets or alphabetical order. So, longest chain, easy peasy. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Which one? It doesn't matter. All of them are going to give you same number of substituents. Okay? But the question is, from where am I going to start numbering? Will I start numbering from my left or should I start numbering from my right? And why?
From my left.
From my left?
Yes. Sorry, from my right.
From the right.
Yeah, because will be two
substituents at the same location. Very good. So I'm going to start numbering from this end. And when you take off from this class, you can always go back and try to figure out other numbering techniques. You can go from 1, 2, 3, 4, 5, or things like that. You can do that. So my root name is pent, and E. Now, how many substituents do I have? I have a methyl, methyl, and a methyl here.
Two. sorry, 2,2,4 trimethyl.
Very good. So it doesn't matter if your substituents are on the same carbon, you have to write them out separately. On the other hand, if you have the same group, you can bulk them together as a tri or a di or something, but you have to write the locations at all times. Okay? Very good. The next part of our context is the nomenclature of branched alkyl groups. And let's see, where is my slide for that? Right here. You are not able to see it. Are you able to see my slide now?
Yep.
Okay, good. So if you look at the branched alkyl groups, we have a lot of variety. But why does this variety exist in the first place? Let's say that we have more than 2 locations. Okay. So in ethyl, we have only 2 carbons. If we have a long main chain, does it matter if our ethyl is connected from the first carbon or the second carbon? It does not matter. However, with alkyls, 1, 2, 3, 4. With alkyls of more than 2 carbons, constitutional alkyls can be formed. So what do I mean? My long chain can be connected from the first carbon. 1, 2, 3, 4. I made an extra carbon, sorry. Or my carbon can be connected from the second carbon. So you see the constitutional nature of our alkyls. So within this alkyl, an internal hydrogen can be removed to form more than one substituent from the same alkyl. Okay. So if you look at this example, and this is a very different kind of an example. I have these 2 substituents, let's say. These 2 substituents. 1, 2, 3, 1, 2, 3. If I have to look at these, both of these groups have 3 carbons on them. But this one is the internal hydrogen. This one is the first hydrogen. So the main chain or the parent chain is attached to which point in this side chain. That is how your name will be decided. Now, if you look back at the screen that I was sharing, there is a complex IUPAC name for all of these substituents, which can be mentioned. However, their common names, which I am showing you on this slide, are also acceptable. Okay. Now, you will have to memorize these structures and you will have to memorize these names also. We will only be looking at the 3-membered carbons, 4-membered carbons, 5-membered carbons, and vinyls and allyls. So all this
Dr.
time,
Verma?
please go ahead.
Dr. Verma?
Yes, go ahead, Makela. Oh, Makela.
So you're saying that if on our drill, we don't say what's on like these examples, they'll be wrong?
For example, what do you plan to say?
Hello?
Yes, Makela, what do you plan to say then? I mean, can you give me an example of what would you say
I
and
was
how?
saying,
Go ahead,
so
go ahead.
like, you know how we have like You know how in the previous example we did like a methyl group, but like what if it's like something else, like it's a 3-carbon substituents? Would you require us to write the other
Isopropyl and
one,
propyl.
like
Yes.
the complex?
Yes.
Yeah. Okay.
Yes. 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 And I'll
In replace of the other.
yes. Yes. So
Okay.
let me just help you see a few of these. Okay. Now I'm going to draw a long chain, very long chain, and we will not care about the parent's name. Okay, I'm just going to draw this so we can see how it comes out. Now, I just showed you these these two versions of the 3-carbon compound. Okay, if you say that if I attach it 1, 2, 3, 1, 2, 3, and I attach it at this carbon, this and this are exactly the same. So there is no other constitutional isomer possible for this alkyl. There are only 2 constitutional isomers possible for a 3-carbon side chain. One of them is just known as propyl, right? The linear one. And this branched one where it is
Isopropyl.
attached, yes, where it is attached to this CH is known as the isopropyl. Now, isopropyl is a very special way of seeing this. You will have to recognize to see it. What if you have a structure like this? Can you still recognize this isopropyl? Think about the Y shape it is taking. And that is where I will help you look at isopropyl. Isopropyl has a CH and 2 methyl groups on it. This is isopropyl. What about isobutyl? First of all, isobutyl will have how many carbons? Isobutyl
4.
will have 4 carbons. I will have this CH with 2 CH3s. So these are only my 1, 2, 3 groups. I will also have a CH2. So 1, 2, 3, 4. These are my 4 carbons. This carbon of CH2
Can
will
you
be,
move your paper up a little bit?
yes, yes. So this CH2 will be inserted between the main chain and the isopropyl to make this side chain as isobutyl. Do you see what I did? So I just inserted a CH2, a extra carbon moiety between this Y fork and this main chain. Can anybody guess what a isopentyl will be?
5 carbon.
5 carbons, same forking,
And attached
CH3,
to CH2.
CH3, yes. And now 2 CH2s will be attached. This 5th CH2 will be attached to the main chain. The only thing is that you have to recognize the structure. So this CH2 between 1 CH2 for isobutyl, 2 CH2s for isopentyl. Do you see that?
Yep.
Now similarly, we have secondary butyl. Now for butyl, we have already seen for 4 carbons, there will be simple butyl, isobutyl, which we have already seen, sec-butyl, and then ter-butyl. So butyl will be your regular 1, 2, 3, 4. Regular linear alkyl group. Isobutyl, we already saw. Blah, blah, blah. Okay, don't worry about how long this is. Isobutyl we have already seen. We will have CH2, CH with 2 CH3s. And then sec-butyl. Let's do the tertiary butyl first. A tertiary butyl will have a carbon with 3 methyl groups on it. So a tertiary kind of a carbon. It's not really tertiary because it is attached to a 4th carbon also, which is the main parent chain carbon. So this carbon, 4 carbons, 1, 2, 3, 4. 4 carbons are there, but there are 3 methyl groups. In iso, you will have 2 methyl groups. In tertiary, you will have 3 methyl groups. What is a sec-butyl? A sec-butyl will have CH, a secondary CH. CH2, CH3, CH3. So this is what a sec-butyl is. It's not really a secondary carbon because it is attached to a 3rd carbon also. Ideally, we should just say that it is a tertiary carbon. However, if you just look at the group, then we say it is a sec-butyl. And then we have a neopentyl. For 5 carbons, you just need to know 2 of these. 3 of these. First is the pentyl. The second is the isopentyl, which we did on our last page. Neopentyl. Neopentyl will be tertiary pentyl, but a CH2 inserted. So this is my tertiary butyl. My neopentyl just has this CH2 in between the parent chain and the other carbons. How many carbons do I have? 1, 2, 3, 4, and 5. And what would be my regular pentyl be? 1, 2, 3, 4, 5. Make sure you know how to count your carbons. Once you're branching away from the parent chain, you have to count the first carbon. So whenever you're going to name these compounds, let's name one of these compound. Let's say we have to name this particular compound. I will give my root name here. I have these 2 substituents. How am I going to use them alphabetically? I will have to use the propyls P and the isopropyls I. Okay, that is the rule that you have to follow. However, the only exception is when you write iso and neo, you have to consider their alphabet. So the I and the N will be used. But when you're using sec-butyl or terbutyl, we always write a hyphen. So you have to write a hyphen, and you do not have to consider sec and ter. Need hyphen and no alphabet. Okay, I want you to remember this exception. I will show you an example very soon. So what is the use of all these alkyl structures? Simple haloalkanes can also be used with the names of these alkyls. So for example, if I say sec-butyl chloride, how are you going to write out this structure? You will first draw your sec-butyl. What does our sec-butyl look like? I'm going to write this CH, CH3, CH2, CH3. Now make sure that you read the question. Is a bond line structure asked or a condensed structure asked? What kind of a structure is asked from you? So this is my sec-butyl. What do I have to attach next to it? A chloride. Isobutyl bromide. How will I draw that? I will have my isobutyl CH with 2 CH3s, 1 CH2 inserted. This is the point of contact. What do I have to insert? A bromide. So this is my isobutyl bromide. Any questions? Okay. How would you draw a 3-bromo? Bromo 2-methyl pentane. How would you draw something like this? You will draw the pentane first. Then you will give locants on it. Once you have given locants, then place the substituents appropriately. Substituents appropriately. These should be your steps. Go ahead and do that and let me know if someone is facing problems. So draw this and also tell me what is the functional group. Of this molecule. Okay. So 3-bromo 2-methyl pentane. Draw it out, then tell me what is the functional group present on this molecule. For cycloalkanes, we will be using similar rules, very similar rule. So first of all, you will find out how many number of carbons are there. How many number of carbons are there? 5. What is the root word for 5 carbons? Pent. However, this is a cyclic molecule. If you compare this linear chain and this cyclic molecule, the HDI for this molecule is 0, while HDI for this molecule without calculation,
1.
Can anyone tell me?
1.
Exactly, 1. So we do not just label them as pentane, we will label it as cyclopentane. That is the only difference. So your root name will be accompanied by a cyclo. If you have a cyclic material as a substituent, and this is possible, what will be the name of this alkyl now? So first of all, how many carbons are involved in this ring?
3.
Very good. So what will be the root name? Cyclopropane. However, just like in your alkyls, when you have propyl, how do you name this? You just write propyl. We will write this as cyclopropyl. Exactly similar. However, just you have to remember, for all cyclic situations, you have to write the word cyclo. So number of ring in the carbon, just similar to the linear chain. And when is your cyclic group going to be a substituent, the time that your linear chain attached to it. So there are more number of carbons in attached linear chain than in the ring. So for example, if I have a structure like this and I have 1, 2, 3. So who is going to be my main parent? The cyclic chain or the side chain?
Cyclic.
The cyclic chain. Why? Because the number of carbons in my side chain are less. There are 3. While the number of carbons in my cyclic chain are 5. 5 is bigger. This is going to be my parent chain. There is one exception, of course. There is always exception. When you have one, two, three. When you have 2 cyclic rings. When you have 2 cyclic rings, it does not matter how big your linear chain is. Now your cyclic rings will become your side chains. So we are going to follow the same pattern. We will first figure out our longest chain. We will then make sure that all the priorities are there, all the maximum number of substituents are there, and then find the lowest locant value. Do you think this is a good idea, or 1, 2, 3, 4? Which locant number should we follow? The red one or the black one?
From the left.
Red one. So this is a butane, but you also have what? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. You have 2 cyclohexyls. How do we write them? Di. Where are they? On the location 1 and 3. So 1,3-dicyclohexyl butane. So when you will have 2 rings on this side chain, you will be giving it naming like this. Most of the time, you will see a cyclic structure with the side chain. How will we name this? Of course, 1, 2, 3, 4, 5, 6. Longest chain, lowest locant value, 1 cyclopropyl hexane. All right, all of you, go ahead and write this name now. And I want you to remember 2, 3, 4. Actually, let's not do this. One, two, three. Now, before you do this, I wanted to remind you, if you have just one cyclic side chain or one linear chain, it is pretty easy and evident that your group, whatever group here is, the cyclopentane or the propyl cyclopentane, you don't even have to give the location, because it will be evident that the only substituent will be counted from your carbon 1. But when you have 2 substituents, you have to make sure that you give them the lowest locant value. So are you going to count like this or anti-clockwise like this? The red one or the black one? Mesha, are you with us? Can you tell me which counting will be followed, the black route or the red route? Okay, anyone else wants to answer that?
Black.
The red.
Okay, if we follow the red, our locant values will be 1 and 4, right? 1 and then 4. So that will be big numbers. But if you follow the black path, your locant values will be 1 and 3. So we have to aim for lower locant values. Now this is when your both substituents were same priority. What if your substituents are similar priority but different alphabetical order? So which group is this? Sydney. Can you tell me which group is this? Looking at the structures here. Sydney, any idea? Okay, how about this one? Maybe this will help us. Anyone?
Sig-butyl.
I'm sorry?
Sig-butyl.
No, this is a hydrogen here.
Ah, this hydrogen. Okay, this
So
is
1, 2, 3. 3 carbons. Very good.
Propyl.
3 carbons are propyl, and these 3 with the secondary intermediate
Isopropyl.
will be isopropyl. And this is where you have to remember the rule that iso and neo, when you have an iso or a neo, you have to consider their alphabet. Now looking at this structure, your propyl starts with the P, your iso starts with the 1. Where will I start my counting? Will I do 1, 2, 3? Or should I do 1, 2, 3? The red or the black?
I start from
Red.
iso.
We will start from the red. Very good. The reason is when you have similar priorities, you will follow the lower locant at that point. When there is a tie, that this substituent can also start at 1, and this substituent can also start at 1. The other substituent can end at 3. The other substituent can end at 3. So you will go with the alphabet at that point. So how will we name this? We will name this as 1 isopropyl,
3 propyl.
propyl,
Cyclopentane.
cyclopentane. That's right.
Pentane.
Very good. So very, very, very similar rules. Just when you have a ring size longer than it, or you have 2 cyclic structures, only then your cyclic structure will be your side chains or alkyls. Let's do one more example before we move on to alkenes and alkynes. So what is here? Instead of having 2, I have 3. First of all, what are my side chains? Are my side chains longer than my cyclic ring? No.
No.
So my side chains will be my substituents. I have a methyl here, a ethyl here,
Chloro.
and a chloro. You have to tell me at which substituent I have to start my numbering.
From methyl.
And from where to where? Will I go towards
1,
ethyl or
yes.
away?
No, from methyl to ethyl.
Now, even though you have a chloro, you have an ethyl, you have a methyl, do not follow the alphabetic route. Follow the lowest locant rule. Always remember that. Yeah, so this will be, of course, this will be written first for chloro, 2
ethyl, 1 methyl, cyclohexene.
anyone has any questions? Salome, are you feeling okay with this?
Yes, ma'am.
Kara, Taylor?
Yes, ma'am.
Okay.
I mean, it makes sense, but like I'll work on it.
Okay. Please go ahead and ask any questions at any point. If we are doing an example and you're not following through, of course, I know this is also too much, but you can just follow the nomenclature rules. You can write them out. You can look at them when you're solving your problem. And then that would help you. Definitely, it is going to help you solve more problems. Okay. So going over our alkene and alkyne groups. Alkenes and alkynes also follow very similar route. However, in your alkene and in your alkyne, our hydrocarbon or the infix will change to En even if there is one double bond. For one triple bond, it will change to Yn. Okay, and of course the suffix would stay the same. So if you look, suffix will change only when you have anything over alkane, alkene, alkyne, and alkyl halides. If you have anything after those, the alcohol, the aldehyde, the ketone, oic acid for carboxylic acid. You don't need to know any of those for now. Okay? You don't have to know any of those. This is just for your viewing only. I'm not going to ask you any alcohols or carboxylic acids, not till we reach organic 2. So if you look at this, and this is just a very general structure, there are 4 carbons, so bute. Throughout the carbon, there is no double bond. This double bond is part of the functional group. It's not part of the main chain. So we will still write a AN. And then instead of writing our simple E for priority, we will end with oic acid. That is the only reason I have this slide here, for you to see how E can change. Okay. So for example, if you're looking at this, we are following the same route. How many carbons are in this structure? 4, which comes to bute. Because there is at least one double bond, we will be writing En. There is no other priority, so I will write E at the end. There are 2 ways by which we can write it. You will have to give the location of your double bond. When you give your location, or whenever you're looking at your double bond or triple bonds, you have to make sure that they have the lowest priority. Lowest locant value. So 1, 2, 3, 4. 1 bute. Or I would write it as 1 En. Both of these are completely correct. So if you compare our rules from the alkanes, we will still be following that same rule. Now let's just use that again. So we just did this one. 1, 2, 3, 4. Bute 1 E. But what if my location of double bond changes? 1, 2, 3, 4. And from the other end, 1, 2, 3, 4. At both the countings, I see my numbering for double bond starts at 2. So bute for the 4 carbons, 2 for the location. Any questions on what I did? 1, 2, 3, 4, 5, 6, 7. How would I name this? 7 carbons. So hept.
2,
Where is the location of my carbon? Will I start
2,
from the other end or closer to my double bond? Of course, closer to
closer,
double bond. And so hept 2 ene. Okay. Very similarly, if I have a triple bond, and my triple bond could be internal or terminal. So this is a terminal triple bond. What does that mean? How many carbons do I have here, by the way? Portia? Oh.
sorry,
Portia, do you understand how many carbons do I have here? Okay, 1, 2, 3, 4. And so I have a bute. I still have a bute, but my carbon numbering will start closer so that my locant value is low. Bute 1, triple bond will come with the YN and end with the E. So this is a terminal triple bond where the triple bond is at the first carbon. I can have a triple bond internally also. Portia, are you still here? Okay, don't worry about that. Hannah, can you answer this question? Hannah
What was
Young.
the question again?
So I want to ask you, how many carbons are in this molecule?
Is it 4?
It is 4. Very good. So this is an example of a internal alkyne. Thank you, Hannah. What is the name that is associated with it? I will still count the carbons, bute. But now my location of the triple bond has changed. So bute 2, 9. Okay. So we just did hept 2 ene. But let's say that instead of these two, I have this molecule. I'm going to follow the same rules. I will first find out my longest chain. I will make sure that my priority is in that longest chain. Which are my priority right now? These 2 double bonds. Then I will also make sure that my locant value is the lowest. It has to be the smallest. So will I start from 1, 2, 3, 4, 5, 6, 7, where my double bonds are at 3rd and 5th position? Or should I count from this end 1, 2, 3, 4, 5, 6, 7? So, Dihaja, are you here?
Yes, ma'am.
Okay, so Dihaja, which locant values should I use? The one in the black or the one in the red?
The red.
Very good. So that my alkene is now with 2nd and 4th, which is smaller than 3 and 5. Very good. So after I followed that, equal substitutions, I also have to remember to write them alphabetically. And if I have same groups, I will write the ditri with them. So if you pay attention to this, I have 2 double bonds. I will be locating both of them. But now with hept 2, 4, di en, no other priority. So any questions? So we are still following the same rules. So if you look at all of these structures, there are more examples that I have on this structure. you can see 1, 2, 3, 4, 5, but I started my counting from the other end. So 1, 2, 3, 4, 5. The second carbon is where my En is. At the third carbon, I have the ethyl group. Now with our alkenes come special isomers. Okay. With alkenes, you will always write the cis and trans isomers. Now, this is the second kind of isomers that we are going to do. Cis and trans are a special type of stereo isomer. If you remember from our module 1, if a compound has same molecular formula, there can be two things that can happen to it. It can have different connectivity, and we say that it is a constitutional or connecting isomer. Do you remember that? There was another relation if they have same molecular formula, that connectivity is exactly the same. So we just said that they are same. Up to module 4, it is completely fine. But now from this point onwards, if the connectivity is exactly the same, however, arrangement of atoms on same carbon is different, we say they are stereoisomers. And our cis and trans, if you have double bonds, we have what is known as the geometrical or the cis or trans isomers. If you have single bonds or sigma bonds only, we will do module 5 for these kind of isomers. So we have already looked at constitutional. Let's start to look at geometrical isomers. Now, how do we recognize geometrical isomers or cis-trans isomers? They will always occur across a double bond. So whenever you're thinking about a geometrical isomer, think about both the carbons across the double bond. Same carbon has two double bonds, a bromine on it and a CH3 on it. Let's say that is happening. On the other, it's just hydrogens. Same carbon, CH3, let's do CH3 so we can relate it. To the other, CH3 is there. To this, H is there. Both of the substituents on this carbon are exactly the same, but let's switch these two. Now you will say, oh, the connectivity is exactly the same. To the same carbon, the bromine and methyl is attached. To the same carbon, methyl and bromine is attached. The relationship between these two should be same. They are same, but geometrically different. If you look at this methyl, it is close to this methyl. But if you look at this methyl, it is opposite to this methyl. And it is pretty easy to see on a planar structure. Remember, sp2 hybridized atoms have a flat planar structure. So if you just assume that I have a C double bond C, and my four corners are some bond. This is the exact way this double bond is present. It is completely flat. all the groups are on the corners of these 4 ends, exactly like this. So I have bromine here, and I have CH3 here, and I have CH3 here, and I have a hydrogen here. So in this location, my CH3 and CH3 have to cross over or are considered in the opposite ends, right? They are the opposite ends. While my CH3 and bromine, they are on the same side, on the same side. And so this is why our cis and trans isomers will arise. Cis and means that both are priority groups. So again, you have to look at both the carbons. Let's look at carbon A. Among this group and this group, the atom which is directly attached to this carbon, whoever has a higher atomic number, so you have to look back in your periodic table, whoever has the higher atomic number will be the higher priority group. So among a hydrogen and a methyl, which will be the more priority group? The methyl. On carbon B, among methyl and hydrogen, which is your priority group? The CH3. Priority groups, same. Methyl, methyl. Same side. So cis or syn. So both of these conditions need to be fulfilled to be a molecule to be called as a cis. Any questions? What is a cis? Let me very quickly introduce you to the Z also. C2H5CH3. First of all, what is the C2H5? If you look at C2H5, it is just a molecular formula. Remember your module 1. How do you write Lewis structures from a given molecular formula? You have your carbons, 2 carbons. You write your multivalent atom first. Then you fill in your hydrogens. Remember to keep the octet. What happened to this third carbon? Instead of attaching to a third carbon, this carbon is attaching to this carbon B. Oops. Do you understand what is this? This C2H5 is actually a ethyl group. So if you compare on Ca between H and CH3, CH3 is your priority group. Between H and C2H5, ethyl group is your priority group. Priority groups are not same. But they are still on same side. And hence, we label this double bond as a Z. So there is not much difference. The only difference is that the groups are different. The groups are exactly the same. This is cis, this is Z. What will be trans? Trans will be something like this. On A, on one of the carbons, you have priority. This is the priority. On this carbon, this is your priority. But priority groups are same. Same priority groups, but on opposite side. So in regular terms, we say they are trans. Actually, Z and syn. So this is your term, trans. When your priority groups across the double bond are exactly same, we call them trans. But when your priority groups are not the same, we have to label them as E or Z. So A, priority group is right here. B, priority group is right here. Do you have, oh, this is different. Different priority group, but also on opposite side. So this stereoisomer will be labeled as a E or anti. So don't forget these terms. We are going to use them again and again. So let's look at this example. And we have already looked at dienes and trines. I don't want to take a lot of time in naming this. 1, 2, 3, 4, 5, 6, 7. There are 7 carbons, so it is definitely going to be a het. At 1, 2, 3, 4, 5, 6. So we have double bond at the first, at the third, and the 5th location. So 1, 3, 5 hyphen triene ending with the E. So that should be the name of this compound. But this naming is considered incomplete. If there is a possibility of any of these enes, alkenes, to be E or Z or cis or trans, you have to write it here. Let's look across carbon 1 and 2. Okay, Armani, are you here?
Yes.
Okay, Armani, I need to your help. Between the carbon 1 and carbon 2, did I draw all my bonds or is there bond hidden also?
I think you drew them all.
So how about this hydrogen?
Oh no, okay.
Right? Okay.
There's
So
one.
across carbon 1 and 2, let's look at carbon 2. On carbon 2, I have a hydrogen and I have this bulky group. Who out of these two will have priority? Armani?
Carbon 1.
So between hydrogen and this bulky group on carbon 2, which of these two groups will be having more priority?
Is it 2?
It is this bulky group. Okay? And on carbon 1, you have these two hydrogens. Do you think you can have a priority here?
No.
No. Very good. Because there is no priority on carbon 1, we cannot label this double bond as cis or trans. So this is neither. Okay, very good, Armani. Thank you. Ariel, are you here?
Yes.
Okay, Ariel, let's look at our second double bond. Do I have all the bonds across the carbon, or are there any hidden bonds also?
I think one is missing on the third C and the fourth C.
Very good. What am I missing on both of these? The hydrogen. Okay, very good. Ariel, now across this double bond, let's look at C3. On C3, I have this bulky group and I have the hydrogen. Which out of these two groups will have more priority, the hydrogen or the bulky group?
Is it the bulky group?
Very good. On C4, so let me just mark it like this. On C4, I have a hydrogen and a bulky group. This is my priority group, right? I hope this will help you see better. What do you think is the geometrical isomer? Is it cis or trans, or E or Z? So can I use cis or trans here, or will I have to use the E or Z versions here?
I think E or Z because it has a CH3 on the other side, on the right side.
Very good, Ariel. Because these two priority groups are not same. They are different priority groups. I cannot use, oh, this is same. Because I have different priority groups on opposite sides, I will be labeling my third carbon to be E oriented. Very good, Ariel. Very good. Thank you so much. Hannah, can you help me with the last one?
Yes.
Okay, so again, Hannah, do I have all the bonds on this carbon, or am I missing any?
Is there one H missing?
Exactly, very good. Now for both of these, let's look at C5. Where is the priority group? The top portion or the hydrogen?
On the top.
Exactly, very good. So this is my priority group here. Where is my priority group across C6?
CH3.
Very good. So are the priority groups same or different?
Different.
Different. So I have different priority groups. Will I be using the cis-trans version or the EZ version?
Is it the EZ version?
Exactly, very good. We use cis-trans only for same priority groups. When priority groups across the carbons is exactly the same. Because your priority groups are different, one is methyl, one is this bulky group. We don't have to know the name right now. So we are going to use the E or Z. So are the priority groups on the same side or the opposite side?
Same.
The same side. Very good, Hannah. And so on the fifth carbon, I have a Z. When you will be naming your double bond, and thank you so much, Hannah, very helpful. You will write them in parentheses like this. You will write the location of your double bond. You will then write your EZ or cis or trans, comma, the next location, EZ or cis or trans. Close the parentheses, put a hyphen. Remember, there is no space. I mean, you can see space here, but there should be no space here. Okay, so this is the name for this particular compound. So when we look at double bonds, you will always have to give their name like this. For cycloalkenes, again, the name is going to be very similar to what cycloalkanes was. What is this molecule? Cyclohexane. What will be the name for this molecule will be? Cyclo, 6 carbons, hex. Instead of a hydrocarbon completely saturated, you see at least one double bond. So the En, no other priority, it ends with the E. So this is the only difference that you see here. The second and important thing about cyclohexene, we always assume that your number 1 and number 2 will be containing the double bond. Always. How does this affect? Let's say that you have a structure like this. How will you label it? Definitely 1, 2, 3, and 4, and so on. So 1-methyl cyclohexene. But what if your methyl is up here? Remember, your double bond needs to be the number 1 and number 2 and number 3. So 3-methyl cyclohexene. Always remember this. This is the only difference that we see between cyclohexane and cycloalkane and cycloalkenes, is that your double bond needs to be the carbon 1 and carbon 2. So these cycloalkene sp2 carbons always have to be designated as C1 and C2 of the ring. And then you follow the lowest locant numbering. An important naming that all of you must know is the 2 sp2 carbons outside. When you have a system like this, you have to recognize this is not any sp2, these are vinyl. So this name will be vinyl cyclohexane. On the other hand, if I have 3 carbons, 1, 2, 3, this is also a special kind of a side group, allyl. So this is known as allyl cyclohexane. Other common names that you must know of are ethylene, which is CH2, CH2, acetylene, which is CH triple bonded CH, 2 carbons, 2 carbons. We also have looked at phenyl and benzyl in module 2. This is a phenyl, 1 hydrogen is gone. This will be named as phenyl chloride. Whereas if outside this aromatic ring, you have a sp3 carbon to which anything is attached. So this carbon location is known as benzyl chloride. This is just a repetition of what we have already looked at. Yeah. Now between between alkanes and alkynes, I have to mention a special time. Remember, how could we miss an exception in alkenes and alkynes? Now, usually, when you will have alkene and an alkyne, between an alkene and an alkyne, usually alkyne will have more priority. So this is the time I'm going to look at my rules again, right here. I have to find my longest chain. My longest chain must have the priority. The locant value, smallest number for all the substituents and priority. So if I look back here, I will be numbering this as 1, 2, 3, 4, and 5. And so looking at this, I cannot complete my name until I have labeled if this double bond is a E type or a Z type or a cis type or a trans type. So I have 5 carbons. Pent. On the 3rd carbon, I have a double bond. On the 1st carbon, I have my alkyne. So 1, YN. And there's no other priority, so I will end it with the E. But at the 3rd carbon, what do I have? Do I have a cis or a trans? Definitely, this is a priority group. On this carbon, this is the priority group, which are in the opposite directions.
Trans.
Means it is a E, yes, or trans. This is the complete name. So this is what happens usually. However, in case of locant tie, what does that mean? Let's say that my triple bond and my double bond, they can both have same location. 1, 2, 3, 4, 5, 6. So my triple bond is starting at 1. And if I count from here, my double bond is starting at 1. In case of locant tie only, the lowest locant will be the double bond. Okay. Now, why is that? I'm not sure about that, but this is how you will have to remember this. Whenever you have a tie, your locant value will be to the double bond. So how am I going to number or name this? I still have a hex because of the 6 carbons. On the 1st carbon, I have the En. On the 5th carbon, I have my YNE. So the naming priority still belongs to the triple bond, but the locant value goes to the double bond. Plus, what about this carbon? Is this carbon a cis or a trans or E or a Z? Neither.
No.
Neither, because even though on carbon 2, I have a priority and no priority, on carbon 1, I have both compounds as same. So this is a neither case. This is the complete name for this compound. Any questions so far? Okay, so I'm going to draw up a structure before all of you go. And I want all of you to think about the name this structure may have. So go ahead and draw this structure on your pages. I want you to think about all the rules that we have studied so far for nomenclature and apply it on this. Is there anyone who still needs to copy this name on the structure? Anyone who still needs to copy the structure? So what would be the correct name for this structure? Think about all the rules that we are following. First of all, figure out the longest chain, right? The longest chain must have what? It should have the priority. It must have your most number of substituents. Then once you figure that out, you have to remember that you have to give the lowest locant value. That is, all the substituents must be given the smallest number. Also, equal priority substituents will be then written out alphabetically, and same groups will be given diatribe. Okay, I'm going to keep this page together and I'm going to launch the ball now. Think about it. I'll give you 1.5 minutes to finish up. Remember, these balls are not just to check your corrected versions. I just want to see how are you thinking also, right? So one thing is for clear, the name of the structure will end with an octane, right? There are 8 and not other way around. 1, 2, 3, 4, 5, 6, 7. I hope no one has chosen that one. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. Choose any one of them. 1, 2, 3, 4, 5, 6, 7, 8. Okay.
Wait, I didn't answer it. Can you bring it back up?
Okay, I will have to relaunch it because the time ended at 2 minutes. Is there anyone who has any problems if I relaunch it? If you don't want to say it out publicly, you can send me a private chat also. If anybody has any problems with relaunching this ball, okay, let's do that again.